Let us draw shear force diagram and bending moment diagram for cantilever beams. Let us say this is the beam given to us and it is subjected to a point load of 3 kN and UDL of intensity 1 kN per meter, and then a point load at the free end of magnitude 2.5 kN. The distances are as follows. Span AB is 1 meter long, BC is 1.5 meter long, span CD is 2 meter long, and span D is 0.5 meter long. First of all, let us apply equation of equilibrium to it to calculate support reactions. Since this is a cantilever, so it will be subjected to two support reactions, one vertical reaction and one moment at the free end as shown in the diagram. So let us apply. First equation of equilibrium is sum of all vertical forces equal to 0, and this will give me, if I take VA as upward as positive, VA is upward, I will take it as positive. So VA minus 3 minus the total UDL will be 1 into 2, 1 is intensity, 2 is the length over which UDL is acting, minus 2.5 kilonewton. So it will directly give me value of VA, which will be equal to 7.5 kilonewton. Now if I take moment about point A using second equation of equilibrium, that equal to 0, so this MA is the reaction, so I will take this MA as positive, which is anti-clockwise. Now due to 3 kilonewton, I'll get a clockwise moment, so minus 3 into 1, and due to UDL also I'll get a clockwise moment, minus 1 into 2 is the total load, and the distance of point A from the midpoint of span CD will be 1 plus 1.5 plus half of this 1, so it will be 3.5. I will mark the distance here, it will be 3.5, and the total UDL will be assumed to act here. Now the last load minus 2.5 into the total span is, the length of total span is 5 meters, so into 5 is equal to 0. So my MA will be 22.5 kilonewton meter. So these are my support reactions, this one and this one. Now we can start plotting the shear force and bending moment diagram. I will plot my shear force diagram here, and the units of shear force diagram will be kilonewton. Now since this is a cantilever beam, shear force diagram will be positive throughout and will be plotted upward, and I can plot my bending moment diagram also at the same time. The bending moment diagram can be plotted here and its units are kilonewton meter. So if I take method of section and cut my first section here, let us say I'm cutting my first section here. Let me show you my positive sign conventions. Here I'm plotting my positive sign convention, S and M. So if I'm moving from left hand side, then I will take this as positive sign convention, and if I'm moving from right hand side, I will take this as positive sign convention. So let me cut section 1-1. So section 1-1 will be 2.5 kilonewton X, and these are my positive sign convention. So S is upward. If I apply equation of equilibrium to this, I'll get S is equal to 2.5 kilonewton over the span. So it is be constant for span DE. So I can plot my shear force diagram here. It is positive 2.5 kilonewton. So it can be plotted like this. Positive, and this is 2.5 kilonewton. So for the same span, if I take moment about point, let us say this is point X, then moment, and this is anti-clockwise, which is to be taken positive. So 2.5 will also generate same moment. So 2.5 into x is equal to 0. It will give me as is equal to minus 2.5x. Otherwise also the bending moment diagram for a cantilever is always negative. So from this equation it is clear that it will be a linear graph and will vary with x, and x will be 0 here. X is starting from here, so it is 0 here and moving towards fixed end of the beam. It is increasing and it will increase up to point D, which is 0.5. So my moment will be moment at free end, which is point E, will be 0 as x is equal to 0 from this equation, and moment at point D will be equal to minus 1.25 if I put x is equal to 0.5 meter in this equation. So this is my moment. I can plot the moment here, so it will be linear, so it can be plotted like this, negative and 1.25. Now for the span CD, it is subjected to UDL over the entire span, so my shear force diagram will be linear under this and bending moment diagram will be parabolic. So either I can use method of points and can find out the value of shear force diagram and bending moment diagram at the point C, or I can use the method of sections just we have done just now. So now I will continue with the method of points. So I'll find out shear force at point C. So I'll find out shear force on the just right of point C. Here shear force on just right of point C will be sum of all the forces, here. I can redraw my beam here, so I would like to redraw my beam. 2.5 kilonewton and 1 kilonewton per meter, so this is 2 meter, and this is my C, D and E, and this is 0.5 meter. So if I add up everything, I'll get my shear force on just right of C. So I'll add up 2.5 plus 1 into 2, so it will be 4.5 positive. So I can plot 4.C that from 2.5 it will go up to positive 4.5 at this location. Similarly, I can find out moment on just right of C, or you can say on just point C. So it will be, because we know the moment will be negative due to these applied forces because it is a cantilever beam, so it will be equal to negative of 2.5 into 2.5. The total distance of application of this load is 2.5 plus 1 into 2 into 1. This distance is 1, so it will be minus 8.25 kilonewton meter. So it will be parabolic, and I can draw it like this, negative parabola, and 8.25 here. Now I have here on span BC, so I can just add to 4.7. I can add, there will be a sharp change under this point in the shear force diagram, so it will be constant between point B and C because there is no change in loading. But as soon as I approach the point C, so my shear force diagram will observe a jump of 3 kilonewton and will become 7.5. We'll acquire a magnitude of 7.5 here, and then for span AB again it will be constant and it will be equal to 7.5 here, which is also equal to the support reaction VA. So this is my shear force diagram here. Now the bending moment diagram can also be plotted in the same way. For this span BC, because it is subjected to point load only, so my bending moment diagram will be a linear curve, and I can find out the value of bending moment diagram under point B. So I can redraw my beam. I'll do the calculation here. I'll redraw and do the calculation here. So this is my point B, so it is subjected to 3 kilonewton, and then I have a point load, and then I have 2.5 kilonewton load, 1 kilonewton per meter. (1.5 meter), 2 meter, 0.5 meter. So B, C, D and E. I can find out moment at B, which will be negative of moment due to 2.5 force. So 2.5 into the distance will be 2 plus 1.5 plus 5. So it will be 4 minus 1 UDL. Total UDL will be 1 into 2. So this distance will be 2.5 into 2.5. So if I add up this, I'll get minus 15 kilonewton meter. Now I can plot this here. It should be a linear variation. So minus this point will be 15, and here at the free end, at the fixed end, my moment will be 22.5 only. So I can, here also the variation will be linear and it will be 22.5, which is also equal to the support reaction 22.5 kilonewton meter. So this is my bending moment diagram at various points A, B, C, D and E, and A, B, C, D and E for a cantilever beam. This is the bending moment diagram. Let us solve one more problem. So here we'll be dealing with the uniformly varying load. So this is the cantilever, and you can see that it is subjected to triangular loading here, like this. So it is, or I can say that this height is 6 kilonewton per meter intensity of loading here, and intensity of loading here is this. A, B and C are the three. These are the various values. Let us find out the support reaction first of all. So using the equation of equilibrium, the reactions will be VA and MA. So taking VA upward as positive, so it will be minus 2 into 10. Now 2 intensity is acting on the whole span like this, and if I find out the difference here, it is 4 kilonewton per meter. So 2 is acting on the whole span, and for the remaining span we have a triangular loading with one side equal to 4 kilonewton per meter. So it will be 1 by 2 into 4, the area of the triangle, into 6 equal to 0. So V will be equal to 32 kilonewton. And if I take moment about point A to find out MA, let us take MA as positive. Then due to this UDL, which is 2 kilonewton per meter acting on the entire span, so I will get minus 2 into 10 into 5. So it is acting on a span of 10, and its CG will act at the midspan. So 2 into 10 is the length of UDL, 2 is the intensity of UDL, 10 is the length of UDL, and 5 is the distance of point A from the CG of this loading. Now let us look at the triangular loading. I'll redraw the triangular loading here once again, which is acting on span AB. This intensity is 4 kilonewton per meter, and this is 6 meter. So first of all I will take the total load. So my total load will be 1 by 2 into 6 into 4. Now I will draw the locations of its CG. The total load will pass through the centroid of this shape, and so this will be 1 by 3 into the base 6 and 2 by 3 into the base, which is 6. So it will be 2 meter and it will be 4 meter. So I will take 2 meter multiplied by 2 meters. I will take this one into consideration and equal to 0. So my MA will be equal to, now let us draw the shear force diagram. Shear force at point B will be equal to sum over the span. So if I redraw the span, it is 2 kilonewton per meter loading. So this is B and this is C. This is free end, and the variation of shear force will be linear, because under UDL the shear force has a linear variation. So shear force at point B will be equal to the total load. So it will be 2 into 4, that means 8 kilonewton, and it will be positive. I can draw it like this. So it will be linear for the span, and this value is 8. Shear force at point A will be equal to the total load, and the total load will be 2 into 10 plus 1 by 2 into 6 into 4. Total triangular load, total UDL, it is equal to 32 kilonewton. Now here the loading is triangular. My shear force diagram will be parabolic for this span. The shear force will be parabolic. So I can draw it like this, or I'll try to draw it up to some scale. So this value is 32 positive, and I can mention on my diagram that this is linear and this is parabolic. A, B and C. This is my BMD, and I'll plot this in kilonewton meter. So I'll find out the value of MB. It is negative because we are plotting for cantilever, and cantilever has negative bending moment. So it will be equal to 2 into 4 into 2. So half of this will be 2. So it is equal to minus 16 kilonewton meter, and it will be parabolic. So negative 16. My value of bending moment will be equal to the support reaction 124 but negative. So MA will be minus 124 kilonewton meter, and it will be a cubic parabola. So minus, and this value is 124 kilonewton meter. So here the variation is cubic parabola because under uniformly varying load the bending moment diagram takes the shape of cubic parabola, and this is